Now in part D of this problem, we're told to let p sub 4 of x be the fourth degree Taylor polynomial for f about x equals 0. So I just want to bring in our work from the previous steps. Now in the previous steps we were asked to find the first four non-zero terms of f of x, and we found them there. But here, now this is a slight change, but you really have to pay attention to it. Here it says let p sub 4 of x be the fourth degree Taylor polynomial. So you have to remember that the first four terms does not equate to the fourth degree Taylor polynomial. Fourth degree Taylor polynomial in this case is only the first three terms because it ends when you have an x to the fourth. So we'll go ahead and write that out. So that would be p sub 4 of x is equal to 1 plus x squared over 2 plus x to the fourth over 24. So that is our p sub 4 of x. Then, using the information from the graph of y equals absolute value of the fifth derivative of x shown above, show that absolute value of p sub 4 of 1/4 minus f of 1/4 is less than 1/3000. Alright, well, let's first talk about this absolute value. Hang on one second. Alright, since we're going to be referencing this graph of the absolute value of the fifth derivative of x, I just want to put a copy of it there onto our workspace. Now, this expression, absolute value of p sub 4 of 1/4 minus f of 1/4. Let's talk about that because this is a very important expression when we're working with series. Remember that every Taylor series is an infinite series, and it equals whatever its function is exactly if we have an infinite number of terms in it. However, we'll very rarely be working with an infinite number of terms, and often we'll truncate after the first 3 or 4 or 5 terms, etc. When we do that, an error is associated. We won't have the exact answer, but we'll have a close estimate. We want to find out how close that estimate is. So in this case here, p sub 4 of 1/4 is the estimate of using p sub 4 to evaluate f of x when x is 1/4. So let me write that up here. P sub 4 of 1/4 is our estimate for f of 1/4. And obviously f of 1/4 would be the actual. And the difference between these is the error or the remainder. And we don't really care whether it's positive or negative. We care about the magnitude of that error. And so we'll take the absolute value of the estimate minus the actual, and this would come out to be exactly the same as the absolute value of the actual minus the estimate. So it doesn't really matter which term we put first there. And you will see something like this is very likely to come up on your test. Now, this brings in the idea of the Taylor series remainder theorem. And the Taylor series remainder theorem it's sometimes also called the Lagrange error bound, and you will see both of those uses on the AP test. The Taylor series remainder or the Lagrange error bound is found in this way. If the error associated with an nth degree Taylor polynomial is less than the first truncated term. So it would be the n plus first derivative. In this case, we're working with 0, centered at 0, over n plus 1 factorial times x to the n plus first, x to the n plus first power. Now, it's not exactly less than that term, and I'm going to change that 0 to be c, where c is some value between x, in this case is 1/4, and the center, which is 0. So I wrote this for the Maclaurin series here, but it's a simple development of this to get this for any Taylor series. So it has to be between a and x. C is some value in between the center and the value that we're trying to evaluate, the x value that we want to evaluate the function at, which in this case is 1/4. So c is some value in there. And what we want to do where c maximizes f to the n plus 1 of x. We'll just use x there. So we want to choose a value for c that maximizes the n plus first derivative. And that value for c will be something in between 0 and 1/4, in between our center and the x value that we're trying to evaluate the original function at. So this is the basic idea of the Taylor series remainder, or what is sometimes called the Lagrange error bound. So what we want here then is to come up with, we know that that error has to be less than, in this case we're using the 4th degree, and so for this particular problem, what that says is that the error for the 4th degree Taylor polynomial has to be less than this 5th term, or the term for x to the 5th power. Now we're not going to use the term for x to the 6th above here. So this is again with a Taylor series remainder. This is slightly different than the way we use the alternating series remainder. If we end at the 4th degree for the Taylor series remainder, then our error bound will be constructed from the x to the 5th term. And so I have the general form of the x to the 5th term listed there. Actually, instead of 0, we need to have our c in there. Alright, well, we can find out what 5 factorial is. We know that that is 120. And 1/4 to the 5th power, and I've already calculated this, but you can calculate it on your own. That is the same as 1 over 2 to the 10th power, and 2 to the 10th power is 1024. And so we would have 1024 there, which is 1/4 to the 5th power. Now the only thing we need here then is a value for the 5th derivative on the interval from 0 to 1/4. And this is where the graph comes in. If you notice on our graph over here, this is the absolute value of the 5th derivative. And I guess we could actually state in here that this should be an absolute value here, an absolute value, and all we need to do is look at our graph to see that on the interval from 0 to 1/4, which would be basically from here, from 0 to 1/4, we can see that the maximum value of the derivative there is less than 40. We don't know exactly what it is, but it's okay for us to put in an upper bound on that at 40. So C in this case is not an actual value between 0 and 1/4 because there is no value for C that gives us a derivative of 40. However, you will see this used, and we will use this strategy to find an upper bound for that derivative there. So the upper bound of the derivative, the fifth derivative of x on the interval from 0 to 1/4 is going to be 40. And so when we put this together, this whole thing becomes 1/3, and 1 over 3 times 10^24 is 3072, which is less than 1 over 3000. And so we've shown that since our error, since we use 40, which is higher than what it actually, it's an upper bound for the derivative there, then our actual number will come in to be less than 3072, but that is well less than 1 over 3000. So this is an example of how the Taylor series remainder works. We could not have used the alternating series remainder here since the first three terms are positive, or in this case all of the terms are positive for p sub 4. It's not an strictly alternating series. And in that case, when we're looking for the error, we will have to use the Taylor series remainder, or what is called also the Lagrange error bound. And it's related to the first unused term. If we stop at 4th degree, we will use the 5th degree term and try to maximize the derivative, the fifth derivative of x on the interval from our center, 0, to the point where we're trying to evaluate that derivative, the original function at, in this case it's 1/4. So we'll stop this at that point, and we will see other examples of how to use the Lagrange error bound Taylor series remainder.